So we've been talking about circles and different properties of circles. I want to review just a couple of things here quick today, and then do an example, as I promised you yesterday, of a circle with a lot of things going on where we have to try to pick out different features. We've mentioned this, but I want to clarify it. If we have a central angle, whatever that angle is, the generic symbol we use for it is that Greek letter theta. The arc out here can be defined in a couple of different ways. One way of defining it is it has a degrees of the same as that central angle. For example, if I say this angle here is 72 degrees, this arc out here is also 72 degrees. Well, we also saw an inscribed angle. An inscribed angle had its vertex on the circle. This angle here is going to be half of theta, half of that central angle. So if I make this inscribed angle here, this arc is called an intercepted arc. The angle of this inscribed angle is half of that intercepted arc. So the intercepted arc is 72 degrees. This is a 36-degree angle. Now there are some consequences of that are a little bit subtle but very obvious once you see them. If I have the diameter of a circle, you might not think about it, but that diameter actually has two intercepted arcs. But let's just use the bottom as an intercepted arc. That's half a circle. That's 180 degrees. So if I have an inscribed angle here, what's this angle have to be? It has to be half of 180 or 90 degrees. And any inscribed angle on that arc will also be 90 degrees. That would be 90 degrees. This would be 90 degrees. Any angle that's inscribed on half a circle, inscribed on the diameter of a circle, if you want to look at it that way, has to be 90 degrees because the intercepted arc is half a circle, or 180 degrees. We saw an example yesterday, actually I think it was a couple days ago, of intersecting chords inside the circle. Now, we used a calculation of, if I know that this is 4, well, let's do this. Well, let's say 4 inches and 6 inches in length for those pieces. If I know this one is 3 inches, this piece here has to be 8 inches because the two chords that intersect cut each other into pieces that multiply to the same product. 3 and 8 are in the same chord. 3 times 8 is 24. 4 and 6 are from the same chord. 4 times 6 is also 24. They cut themselves into pieces that have the same product. But there's another thing that we can use those intersecting chords for. Intersecting chords, I should say. If they intersected at the center of the circle, move that a little bit. Pretend that looks like the center of the circle. If they intersected at the center of a circle, this arc and this arc would be the same because of our vertical angles. This central angle and that central angle would have to be the same. Likewise, this angle and this angle would have to be the same, making these two arcs the same. So the central angle here would just be equal to that arc, of course, because it's a central angle. But what if they don't intersect at the center of a circle? Well, notice the center of the circle somewhere over here, we've moved our intersection away from the center of the circle. And you'll notice what happens is this arc got larger, this arc got smaller as we moved away from the center with our intersection. The total of the two arcs remained the same. So this angle here, theta, if I call this arc A and this one B, that angle, theta, is the average of the two arcs. We add them together and divide by 2. So if I have this of 26 degrees and this over here of 72 degrees, I want to find this angle right here. So this is an interior angle for intersecting chords. That angle, I'll label it theta again, is simply 26 degrees plus 72 degrees divided by 2. 26 plus 72 is 98 degrees divided by 2, makes that angle 49 degrees. We might have chords that don't intersect in a circle, inside the circle, but are still not parallel. If we extend those chords to make secants, remember a secant contains both points that are both inside and outside the circle. If we extend them to make secants until they intersect, we form an exterior angle or a secant angle out here. Now, if we look at the size of that angle, if I know that this arc over here, let's say that that is 68 degrees, I know that the central angle on that arc would also be 68 degrees. And I know that the inscribed angle on that arc would be half of the 68 degrees. It would be 34 degrees. Well, this secant angle out here is smaller than the inscribed angle. How do we know how much smaller? Well, as we move that secant angle further out from the circle, this arc over here stays the same, but this arc will get larger. So the larger this arc here is, the smaller the angle gets. So we use a combination of the two arcs again to find that angle, only now I'm going to label this angle alpha. It's another Greek letter that we use for angles. That angle alpha is not the sum of the two arcs anymore. It is the difference of the two arcs. So let's say that this over here is a 32 degree arc. My angle alpha is the big arc of 68 degrees minus the little arc of 32 degrees and divided by 2. So 68 minus 32 is 36 degrees. Divided by 2 is 18 degrees. So our secant angle out here is 18 degrees. And the final type of angle that we discussed earlier in the week was that tangent angle. So the vertex is still on the circle, but one side of the angle is a tangent. Well, this angle, believe it or not, stays the same no matter where that vertex is on the circle, as long as it intercepts the same arc. So let's say that this arc right here is 110 degrees. If I had an inscribed angle like this angle would be half of the arc. Half of 110 would be 55 degrees. If I move it up here, it's still 55 degrees, half of that arc. If I move it down here, it's still 55 degrees. And as I move it all the way so that it's hitting a tangent rather than having a second chord inside the circle, the angle still does not change. It is still 55 degrees. Even though one side of that angle is outside the circle, the vertex is still on the circle. So it is still really an inscribed angle mathematically. It's not technically an inscribed angle because both sides are not inside the circle anymore, but it's still half of that intercepted arc. So let's have some fun with this.
Katniss, come on.
So, oh, that's ugly. If I tell you that this angle here is 88 degrees, and I tell you that this angle in here is 54 degrees, I want to find this angle here. I'll call that angle A. And I want to find this angle here. I'll call that angle B. Some of those lines look a little curved. Pretend those are all straight lines. So there is kind of a mess going on here. And let's take a look and see what we can figure out from this. Well, first of all, we know that this arc up here is an 88 degree arc because the 88 degrees is the central angle. That has to be, somebody's getting a pretty bad echo. If you want to make sure your mic is muted. So anyway, that has to be 88 degree arc because it is on that central angle, is intercepted by that central angle of 88 degrees. We can find angle A very quickly now because that is a central angle intercepting that same arc. So it is simply half of the 88 degrees. So that is 44 degrees. So like I said, one of the hints I gave you yesterday was just find some way to highlight the pieces that you're looking for. I could redraw the circle over here with just the pieces we were using. This was 88 degrees. We're looking for this angle A here. That makes it a little easier without all the other mess in there to figure out what it is we're working with. Well, now let's take a look at what that 54 degrees tells us. In order to find angle B, we have this big arc out here. We would need to know this little arc. Now that might be hard to see, so again, let me redraw that with just the pieces we need. We know that this is 88 degrees out here. This is angle B that we're trying to find. We would need to know this arc here. Well, we don't know that arc. So the question is there a way to figure out that arc? If I focus on these two lines here, draw this again with just those 2 lines in it. This arc here is that arc that we need. And I know that this angle is 54 degrees, and I already know that this arc out here is 88 degrees. So this other arc over here, if I just call this arc D, I know that this interior angle is those two arcs added together and divided by 2. So I know that D plus 88 divided by 2 gives me that 54-degree central angle. So now I have to work backwards to find that missing arc. So I'm going to multiply by 2 on both sides. D plus 88 is 108. And then I will subtract the 88. So D equals 20 degrees. So this arc here is a 20-degree arc. So back to our original picture, this is a 20-degree arc. Or I can go over here and label it 20 degrees. Now to find angle B, I have, this is a secant angle. I have the big arc and the little arc. I know that angle B, simply the big arc of 88 minus the little arc of 20 divided by 2. 88 minus 20 is 68. 68 divided by 2 is 34 degrees. So this angle out here will be 34 degrees. Are there other things that we could find out about this circle? Well, there sure are. We know that this is a diameter of the circle because it's a chord that goes through the center. So we know it cuts the circle in half. So if this arc is 88 degrees, this arc up here has to be 92 degrees. Those two arcs, if they make half a circle, have to add up to 180 degrees. Looking at it, I think that's about all we know about this circle. I don't think we can find anything else at this point. Pretty sure we can't find anything else at this point. That's about it. But there are pieces you can break down. So let's take a look at a really kind of clustered problem here. I'm going to go to the top of a new page just so I have a little bit of room to scroll. This is one of my favorite types of problems just because it's, well, it's ugly. We'll call this point C. Point A, we'll call this one point F down here. Those are tangent lines, by the way. Make that a diameter. We'll call the center here O. Let's do D. We're going to make those perpendicular. Call this point E and point J. Oh, what else can I do on there? Oops, let me do this. I'm gonna change this just a little bit. I'm gonna move my point B just a little bit to make it a little less cluttered. I'm actually gonna call this point D here. And I'll separate this to two different pieces, so this is point J. And then we'll just connect that across there for fun. See what that does. So I'll give you a second to make sure you get that drawn. So now let's look at what information we are given here. I am going to give you that arc DA 70 degrees. What does that mean? Well, that means from here to here, that's a 70-degree arc. Got to label this point up here G. I'm also going to give you that arc EG is 120 degrees. That means that from here to here, that's a 120-degree arc. I'm going to give you that angle ACF. So here's ACF. So we're talking about this angle right here is 30 degrees. I'm going to tell you that the length OG is 3 centimeters. In other words, the radius of the circle is 3 centimeters. I already gave you this. I already wrote it in, but we'll write it down here as a given that OF is perpendicular to EJ. That's that right angle I already put in down here. So those are all 4 right angles going around there. And finally, I will give you that EK, I'll label this point in here where these intersect K. EK equals 2.5 centimeters. So I'm going to ask you to find a few things here. First thing I'm going to ask you to find is relatively easy. Find the length GF. Well, GF, that's just from here to here. That's just the diameter of the circle. We were given that the radius is 3 centimeters, so the diameter is just double that. It is 6 centimeters. The second thing I'm going to ask you to find is angle EDA. I'll give you a few seconds to look at it, see if you have any ideas on it before we find it. So angle EDA is this angle right here. To know that angle, it is an inscribed angle. Its vertex is on the circle. If I knew this arc all the way around here, that angle would just be half of that intercepted arc. But right now I don't know the arc. I do know that this piece is 120 degrees. If I knew that piece, I could just add them together to get the whole arc. Well, I can find that piece because, and we're going to stretch this a little bit, this right here in red forms a 4-sided figure. We know that a 4-sided figure remember, the interior angle sum for any figure is the number of angles times 180, then minus 360. So 4 times 180 minus 360 gives us 360 degrees total. Since we have tangents here, that's a right angle, and this is a right angle down here, and we know this is 30 degrees. So that tells us that this angle in here has to be 150 degrees. What good does that do us? Well, knowing that that's 150 degrees, and this is a diameter of a circle, and a diameter of a circle, of course, well, one, it's a straight line, but it also splits the circle into 280-degree arcs. Being that that's a line, the 150, this has to be its supplement, or just 30 degrees, which means this arc up here is also a 30-degree arc. So now back to what we're focusing on, this angle right here. Now, it's very convenient for me because I have the use of color. I can highlight what we're looking at. But that angle is inscribed on this intercepted arc, which is just going to be the 120 plus the 30. The 120 plus 30 is 150. 150 divided by 2, 75 degrees for that angle. Wasn't necessarily simple, but it wasn't terrible to get. Next, I'm going to ask you to find angle EHF. Let's erase this here. Where is point H here? Forgot to label it, that's why. There's point H right there. So angle EHF is this angle right here. So it's formed off of these two intersecting chords. I'm looking for that angle right there. Well, how do I look at those intersecting chords? Well, I know this piece up here is just the 30 plus the 70, or 100 degrees. And I know that this piece down here adds with the 120 to make a half circle. So that piece is just 60 degrees. So this angle is a central and interior angle on intersecting chords. It's on a 100 degree and 60 degree arc. Since it's an interior angle, I add the arcs together. So it's 100 plus 60 divided by 2. 100 plus 60 is 160 divided by 2, makes that an 80-degree angle. If I ask you to find the circumference of this circle? Well, we already found up here that diameter is 6. Circumference is just going to be pi times diameter. Pi times 6, or 19 point, what is that? 18.84, sorry. Centimeters. I want you to find arc ADF. Arc ADF goes from here to here. I'll give you a second to look at that and see what you can come up with. Oh, since we know that GF here is a diameter of a circle, we know then that this over here is a half a circle, which would be a 180-degree arc. We have the 30-degree arc here, so we subtract that from 180, tells us ADF is 180 minus 30, or 150 degrees. We already found this one, arc EF, but I want you to find it in centimeters. Rather than the degrees, I want you to find the arc length. Well, we said earlier that arc EF here was a 60-degree arc because it has to combine with the 120 to make 180 or make a half circle. So that's a 60-degree arc. So we're going to take our circumference from problem number 4, 18.84 times 60 out of 360, giving us a 3.14 centimeter arc. Let's talk about the area of sector GOA. So GOA is this sector right here. It's a 30-degree sector. So I have the area of the whole circle, pi times 3 squared, 28.26. That's going to be centimeters squared. So the area of the sector is that area of the circle, 28.26, times that was a 30-degree angle, 30 over 360. It was 2.355 centimeters squared is that area. Angle OFC. Here's angle OFC. I'll do that in red so you can see it a little bit better. This one should be pretty obvious to you. What's that angle have to be? We already marked it. It's 90 degrees. OF is just a radius of a circle. FC is a tangent to the circle. The radius has to be perpendicular to the tangent. I want you to find the length of KJ. Well, here's K and J, so that's that length right there that I'm asking you to find. Well, we told you before that EK was 2.5 right there. If this radius hits that at a right angle, it cuts that chord in half. So KJ is also 2.5 centimeters. Last but not least, let's find angle ABD. So that's simply this angle here, ABD. Now, really, what I need is I need to extend this like that. I know that this arc out here was 120 plus 30, or 150 degrees. I know this arc in here is 70 degrees. Now, even though this side of that angle is a tangent rather than a secant, it still is an exterior angle. So it still is half of the difference of the arcs. So it'll be 150 minus 70. And divided by 2. So it's 80 divided by 2, or 40 degrees. Now, I realize that's a clustered picture. There's a lot going on there. Trying to pick out those pieces is kind of a pain. Since we got a few minutes, let's try one more thing. Let's find the length KF. So KF, that's just this length right here. We know that GF is 6 centimeters. That is just the diameter of the circle. We know that EF is 2.5. How would we find KF? Well, I'm going to let that length be X for right now. So here's my circle. I know my diameter is 6 centimeters. I know this is 2.5, and this is also 2.5 centimeters. I want this to be X. That means this length here is 6 minus X, 6 centimeters minus X. I know that the product of the pieces of chords is the same for intersecting chords. So this chord here is broken into 2.5 and 2.5. This chord is 6 X and 6 minus X. Well, 2.5 times 2.5 is 6.25 times, equals X times 6 minus X. I'm going to distribute the 6, or the X. That's 6X minus X squared. This is a quadratic equation. If I want to solve that, I need to rearrange it so that everything is on one side and the other side equals 0, but I want to do it so that the X squared is positive. So that's negative right now, so I'm going to move everything over to the other side. So I'm going to add X squared to both sides, and I'm going to subtract a 6X from both sides. So now on the left side we have X squared minus 6X plus 6.25 equals 0. Now at this point, we have not learned in either of our classes here how to solve a quadratic equation like this. And occasionally we have time in the fall semester to look briefly at quadratic equations, but even then we only do it by factoring, and this equation is not factorable. So to solve a quadratic equation that isn't factorable, there's a formula called the quadratic formula. To use that formula, we define each of the numbers here. We assign it to a variable. There is no number in front of the X squared, so that's really 1. It's implied to be a 1. So that's going to be the value of A. This is negative 6 times X, so B is going to be negative 6. And our constant is 6.25, so that's going to be C. So the formula is the opposite of B plus or minus the square root B squared minus 4AC all over 2 times A. This is called the quadratic formula. If you took Algebra 2 in high school, you probably saw it. Most likely forgot about it by now because it's not something you use very often. We've made it for 22 weeks of math without having to use it up until this point. So let's plug in. B is a negative 6, so opposite B would be a positive 6, plus or minus 6 squared minus 4 times A is 1 times C is 6.25 over 2 times A is 1 again, so 2 times 1. Well, in here, 6 squared is 36. 4 times 1 is 4. 4 times 6.25 is 25. Bottom 2 times 1 is 2. 36 minus 25 is 11. So that's 6 plus or minus the square root of 11 over 2. So we'll do the square root of 11 quick, which is 3.317. So this is 6 plus or minus 3.317 over 2. Let's do the plus first. 6 plus 3.317 over 2 is 9.317 over 2, which divides out to be 4.6585. That can't be, because The radius here is only 3 centimeters. Can't have that piece be bigger than the radius. So let's do the minus. 6 minus 3.317 over 2. Well, 6 minus 3.317 is 2.683 over 2, which divides out to give us 1.3415 centimeters. That makes sense. By the way, this is actually this other piece. This piece here is the 4.6585. The piece we wanted down here is the 1.3415. Now again, I wouldn't ever ask you to do that. When I started that, I didn't realize that was going to be a quadratic equation, but it's not terrible if you know that formula. Okay, with that, I will shut up. I think I've done enough damage for the day. You have a packet out there. In the packet, it is page 315. 1 through 26 are the problems that deal with these arcs of the circles. There's a quiz out there, by the way. I don't remember if it's for today or if I left it for Monday. Let me double check here quick. Looks like it'll be for Monday. Actually, I don't have it out there yet. I will make sure I get it put out there later today. There will be a quiz out there for Monday on all these arcs. So if you get a chance, look ahead while it's still fresh in your mind. I'll get it put out there this afternoon so it's out there for you. Anybody have any questions? Okay, so we got about 7 minutes left. I'll let you guys have that time to get started on your homework if you wish. Otherwise,